Okay, so now that we're familiar with separable differential equations, we're going to take a look at a specific application, and this is our integrative activity. So it is exponential growth or decay. Now this is very much going to be something that you have seen before, that you have worked with before, but we're going to look at it as a separable differential equation and look at how to solve that differential equation. So the first thing here, exponential growth or decay is said to occur at any time that the instantaneous rate of change of a quantity with respect to time is proportional to the quantity itself. Now here I want to take a look at what this actually means as a differential equation. So the first thing is that here we're looking at the instantaneous rate of change. So what is the instantaneous rate of change with respect to time? That's going to be the derivative with respect to time. So if our quantity, let's say, is y, then we are saying that dy dt, that is our instantaneous rate of change with respect to time. It has to be proportional to the quantity itself. So first off, what does it mean to be proportional? Well, if it is proportional, it means that it's going to be a constant multiple of. So here we end up with the derivative being a constant multiple of the quantity itself. And what is our quantity? Here we're working with our quantity being y. So for exponential growth or decay, this is our differential equation that we're starting off with. We have the derivative is proportional to the quantity itself. dy dt is equal to a constant multiple of y. Now we're interested in modeling exponential growth. So here let's take a look at what are going to be the solutions to this differential equation. So here we have the solutions, and the solutions to this differential equation are given by this. We have y is going to be equal to, again, y naught e to the kt, where y naught is simply just y0. It is the quantity at time t equal to 0. So fine, but let's actually go through and prove this. Okay, let's start with our differential equation and solve it and show that these are going to be our solutions. So let's set it up. We have here dy dt is a constant multiple of y. We are also given here an initial value. So we have that y at time t equal to 0 is equal to y naught. And so here, let's deal with our differential equation. The first thing we want to do is just bring the t's over to one side, bring the y values over to the other side, and that constant k, we can do whatever we want with it. Let's just sort of leave it as is. You could bring it to either side. For now, we end up with dy divided by y is equal to k multiplied by dt. We've completely separated here the variables y from t, and now we are ready to integrate. So on the left-hand side, we have ln absolute value of y is equal to the antiderivative on the right. So here we just have the constant k, which we know the antiderivative will just be k multiplied by t. So we have k multiplied by t. We put in the plus c. Now let's solve for y. So we get rid of the logarithm. We have absolute value of y is equal to e to the kt plus c. Let's drop the absolute value. We end up with y being equal to plus or minus e to the kt plus c. And for this, we're looking at applications involving population growth, for example. We're not going to be looking at here the negative solutions. We're only going to be looking at the positive solutions. So let's just make a note of that. That for us, y is going to be strictly larger than or equal to 0. And so we'll be looking at the positive solutions. So y is now equal to e to the kt plus c. Okay, fine. except that there's a couple things missing. Remember what we're trying to get to here. We want to get to this. We want to have y naught e to the kt. Okay, so there's one thing here left to do, and we want to solve for that value c. Okay, because right now we have our general solution. Let's find the particular solution satisfying this initial condition. So fine. Let's start by looking at this right here. We want to solve for c. And we're going to do that using our initial condition that y of 0 is equal to y naught. And right now we know y is equal to e to the kt plus c. So actually, let's just rewrite this using property of exponentials just quickly. We have e to the kt multiplied by e to the c, remembering that when we multiply these two together, we will be adding the exponents. Okay? So fine, this is what we end up with, and now we can go and use our initial condition, y of 0 is equal to y naught. So really, plugging that in, that's t equal to 0 and y equal to y naught. So that's e to the k multiplied by 0 multiplied by e to the c, which gives us that we have y naught is equal to e to the 0, e to the c, but e to the 0 is just 1, so y naught is going to be directly equal to e to the c. And now we are pretty much done, because this then says that y is equal to e to the c times e to the kt, which really means we have y naught e to the kt. And that is very much the solution that we were looking for. Okay, this is going to be how we refer to our solutions of exponential growth, exponential decay in the future. So one of the questions you're maybe wondering is, what is this constant k? What is this constant representing? So that's very much what we're going to look at. What is the significance of this constant k in this differential equation where dy dt, the derivative, is a constant multiple of the given quantity? So if you solve for k, you end up getting that k is the derivative divided by the current amount of the quantity, which is y. And so we're often going to be referring to the constant k as the relative growth rate. Okay, and actually another way of referring to exponential growth or exponential decay is to say that you have a constant relative growth rate. So if we look a bit closer at k, if k is positive in your differential equation, then you are going to be having exponential growth. And if k is negative, you're going to be having exponential decay.